Okay, I think we'll go ahead and get started again here. I'm gonna have a seat. So Cortland Beyer is our research and water quality guru. Sometimes we refer to him as the mad scientist. I think we're going to start calling him the happy scientist, though. He doesn't like the mad part. But Cortland focuses on water quality for us. He has a background in chemistry and has a good understanding of what chemistry or what chemistry is doing in our water and how that's impacting what happens in the soil. So with that.
Okay, well, appreciate everybody coming out today, and we'll kind of get started here. I do want to talk a little bit about water quality and how it affects our soil and our irrigation systems and the nutrients associated with that. The first thing I want to talk about is where water comes from and how water ends up being what it is, right? So when we poke a hole down into the water or down into the ground and start pumping some water out of it, the water that's down there came there from the rainwater. So as rainwater hits the ground, it goes into the soil, and as it's in the soil, it's taking on the minerals and the other characteristics of that soil. It's coming into the water. And then, of course, as it continues to go on down through sand and gravel and gets down into the aquifer, the journey of that water is kind of found in the water itself, right? So if it goes through a limestone shelf, it's going to take on limestone, and if it's sitting in a gypsum aquifer, it's going to take on gypsum. And so when we drill a well, then we test that water to see what's in there. And one thing before I leave this slide that I do want to mention is that when we first start to pump water out of an aquifer, we're pumping it from right around the base here. But when we begin to irrigate heavily through the season, and we're pumping water day and night for weeks at a time, we get this cone of depression. And so water starts coming from further away and higher than it did when we initially started pumping just down here. And then there are also places in aquifers that sometimes we call underground rivers or paths where water might be coming from somewhere over here. And maybe there is some kind of a crevice or river that's running over here. And so maybe as we start pumping this water, all of a sudden water will kind of start coming in from a different area. And so the water we initially tested was water that was right here. But if we take a water sample in, say, the end of July after we've been pumping a lot, that water could be coming from somewhere else, and that water could look very, very different. And so it's important as we get further into the year with irrigation that we take a water sample to see what that is, especially if there are some potential issues associated with our water. So this is what a water sample looks like. We test for about 14 different minerals, and they tell us a lot about what's going on with your water and how that's going to look on your field, right? So when we irrigate water into your soil, the plant uses the water or it evaporates, and then the water's gone. But the other stuff that was in the water, that stuff stays there, right? And even though we don't think about that as being a lot of bulk, it can be based on the water. So for example, in this water sample, there is 111 parts per million of sodium, which is really high, and the bicarbonate level in this water is 450. And so as a rule of thumb, if you irrigate 9 inches of water, you can take that part per million number that you get and you can multiply that by 2. And the answer you get from that will tell you about how many pounds per acre of stuff you put on. So for example, in this sodium example here, if it's 11 parts per million, in the pounds per acre, if we irrigate 9 inches, that's 222 pounds of sodium per acre that we put on. Okay. So in the case of nitrate here, that's 3.5 parts per million. You put 7 pounds of nitrogen on. So, I mean, it helped a little bit, right? So some of the stuff is good and some of the stuff is bad. And so the good stuff that's in your water is the nitrate, potassium, boron, calcium, sulfate. Those are good things. Sometimes boron can be too high, but boron's usually pretty good. And then the bad stuff that's in our water, sodium because of its nutritional value or anti-nutritional value, iron and manganese because of their potential plugging problems with drip tape, and then iron bacteria for the same reason, and then bicarbonates. And bicarbonates tie up cation fertilizer in the soil. And so again, over time, that can become kind of a problem. So I want to split now this presentation into two different directions. I want to talk on one hand about the nutrition part of the water, and the other I want to talk about the plugging risk associated with water. So as far as the plugging is concerned, we're looking primarily at iron, manganese, and bacteria that would be associated with the iron and manganese. And these show up in our tests. And if we see initial values of iron being about 0.3 parts per million, manganese about 0.15 parts per million, or if there's bacteria present, this is just going to kind of give us a little bit of a flag to say we're going to need to watch what's going on here. Okay. And so, and then if we have bicarbonates that are above 250 parts per million, we're going to need to look at these, and the greater they are, the more of them that there are present, then the more aggressive we're going to need to be as far as potentially treating this water. So I'd like to move now to the nutrient part. The first one I want to talk about is sodium. And sodium will decrease plant available water. It also reduces soil permeability. And like Kurt mentioned earlier, if we have enough sodium in the soil, which we get there from the water, if we've got sodium in our water, sodium looks to the plant a lot like potassium. And if you look on a periodic table of elements, potassium and sodium are right on top of each other, and they look a lot alike to a plant. And so plants will take in sodium and try to use it like potassium, but of course it doesn't work out, and so that can be harmful to the plant. And then sodium also interferes with nitrogen take up, which can be a problem. The next mineral I want to talk about is bicarbonates. So a bicarbonate is an HCO3. If that means anything to anybody. And it's the back half of limestone. So limestone is calcium carbonate, and when those separate in water, the carbonate becomes a bicarbonate, and the calcium ion is kind of hanging out as a calcium. But as you can see, this is a map of hard water in the United States. And when we talk about hard water, typically we're talking about either calcium or magnesium. But for agricultural purposes, those calcium and magnesium minerals or ions are hooked up to a bicarbonate. Okay. And so in our drinking water at home, we actually get rid of the calcium and magnesium with a water softener. But we're interested in keeping the calcium and magnesium in the field because those are nutrients to us. It's the bicarbonate that causes us the trouble. But you can see here, depending on where you live, we have fairly hard water here, and Nebraska has kind of been blessed with a little bit better water than us, and we see that. But so that's just kind of a general idea there. And again, I've put the bicarbonate level of 200 parts per million here just to note again that that's kind of a level where we need to be thinking about that from a plugging and a nutritional perspective. And this is a closer up picture of the pivot field that we talked about earlier today that Kurt mentioned. It's just a couple miles north of here. And this field's been irrigated for 30-ish years, maybe not quite 30. And we've been irrigating with surface water. We don't usually think of surface water having a lot of bicarbonates in it, but we've come to find that there is. And 2 years ago, when we had a lot of rain, or an adequate amount of rain, we really didn't do a whole lot of irrigating. We found that this circle, as you can see here, the outside of the circle in some areas performed better than the inside of the circle did. And after doing the testing that Kurt brought us through, we found that it was the calcium that got tied up by bicarbonates. And so usually you don't see the bicarbonate problem being a problem initially when we put on water, but it's the buildup that year after year after year that those bicarbonates end up staying in the soil. Some of them will leach with rainwater, just like some salt will leach with rainwater. But if we've got more bicarbonate in our water that we're irrigating on than the rainwater can take away, then we're going to start having a buildup. So as far as the solutions are concerned here, if we've got iron and manganese and or manganese in our water, the way that we take care of that problem is either to oxidize those minerals so that they can be filtered out and then filter them, or we need to sequester them, and that's just a fancy chemical name for chelation, where basically there are other chemicals that come around those minerals, keep them from oxidizing until they leave the drip system, and then they can oxidize and do whatever they want because they're not going to cause plugging. So we can do that with sequestering agents. We can oxidize them with special sand, with chlorine, and then acid or a sulfur burner can also be utilized in cases where I don't have a whole lot of iron, but and probably no manganese in a situation like that. So there are a couple different options there. And again, depending on the numbers, we can take care of those issues at an appropriate level. Moving to salt, sodium has to be leached out of the soil. When that water has sodium in it, we put it on the ground. That sodium's not going anywhere but down. And so there are a couple ways that we can assist that process. If we put gypsum on our soil, gypsum is calcium sulfate. The sulfate part of that gypsum is going to hook up with the sodium, and it's going to help to leach that faster because sulfates like to leach. Sulfuric acid does the same thing. It's got sulfates in it. And then we can also use a sulfur burner. We're burning sulfur, sulfates become available. They hook up with the sodium and they leach out of the soil. Bicarbonates are a different issue. The bonus of bicarbonates is that when you react a bicarbonate with acid, bicarbonates turn into carbon dioxide and water. And so it actually leaves the soil. So carbon dioxide gases off and the water just stays in the soil and becomes water for us. So we just need to lower the pH of the soil, and we can do that with sulfuric acid. We can do that with a burner. And again, gypsum is another way that you can get rid of bicarbonates, because even though gypsum isn't a low pH mineral, when it gets into the soil, the bugs in the soil will convert the sulfate actually to sulfuric acid, and so that same reaction occurs. So drip systems all have filtering systems, and anytime we've got an issue where we've got some iron or we've got some manganese, it's important that we use sand filtration because it has an ion exchange capacity that disc filtration doesn't have. And so because of that, it's important that we use sand filtration. There are some special sand media that we can use that can assist and catalyze that reaction, make it happen just a little bit faster, and it's a little bit more efficient. We don't have to use as much of an oxidizer to make that happen. The oxidizers that we use in situations like that would be chlorine and hydrogen peroxide, and we use those in 2-3 parts per million, so we're not having to use a whole lot of that. And then the other solution that I specifically talked about is a sulfur burner. This machine here that you're seeing is a sulfur burner. You're basically making your own acid in the field instead of buying acid, and so it actually becomes the cheapest source of acid. You got to buy the machine, but then you've got a really cheap source of acid, and it's a great way of getting sulfur out into your field. So the way a sulfur burner works is there's this tank on the backside that you can't really see because the plumbing's in front of it. But elemental sulfur, 99.9% sulfur, is loaded into this tank. And there's a little tunnel that it comes across and gets into this burn chamber. Sulfur is lit on fire, either by a heat rod or with a torch, and sulfur burns as a fuel. It's its own fuel. The burning reaction of sulfur creates sulfur dioxide, which travels up this pipe here, comes around in where the water meets it, and that SO2 gas and the water together make an acid called sulfurous acid, which is a weak form of sulfuric acid, comes dumps in this tank here, and then this pump pumps this back into your system. So that's how a sulfur burner works. And basically it changes the lime or the hardness of your water into gypsum. It lowers the pH of your water, so you can leach you can leach sodium from the soil. And then this also gives you the benefit of adding anhydrous ammonia to your irrigation water. So you can use that as a nitrogen source, whereas without acidifying your water, if you would add anhydrous ammonia to your water, the bicarbonates are going to precipitate and plug everything up. And so this is some research that we've been doing to see how much we can add and what pHs we need to be at to make that happen. But it's an opportunity, especially in late season, to get ammonitical nitrogen into corn to boost those nitrogen levels. One more thing that I want to talk about here with sulfur is, as we look at this uptake graph of the sulfur, you can see that about maybe 500-ish GDUs there, V6, V7, we start seeing this steep uptick of sulfur being needed, just a few pounds here early, and then all of a sudden, up it comes. And the bonus of having a sulfur burner is that if you've got some planter applied sulfur, which a lot of times if you're using zinc sulfate, or even if you're putting some AMS, or however you're applying sulfur with the planter, that sulfur will get you, to this 400, 500, 600 GDU spot here. And then when you start irrigating around this time, and you use a sulfur burner, you're now providing a consistent source of sulfur every time you're irrigating, right up until the time until the crop no longer needs water, no longer needs sulfur. So the sulfur burner is a good companion nutritionally. Not only does it keep your lines clean, not only does it keep the bicarbonates out of your soil, but it's also a good companion, nutritional companion to the rest of your system. So I've done a little bit of a cost comparison here, just so you guys can have a general idea of what this what a sulfur burner would cost over I've done this over 10 years here, and if we take 160 acres with an SW500 sulfur burner, and we want to apply 75 pounds of sulfur per acre. Sulfur is about 25 cents a pound, and it's 99.9% pure. So for every pound of sulfur that you burn, you're putting a pound of actual S out onto the field. You're putting it down as sulfate and sulfite. If we use sulfuric acid to do the same thing, there's about 5 pounds of sulfur in every gallon of sulfuric acid. And if we use AMS to put our sulfur on, it's going to take about 480 pounds of, there are 480 pounds of sulfur per ton of AMS. And so if we look down here at the numbers, the initial cost of a sulfuric acid system, you would be pumping sulfuric acid in. That little pump costs you about $1,000. And to get 75 pounds of sulfur on 160 acres, you'd be looking at about $20,400 for sulfuric acid to do that. So your first year of cost is going to run you this $21,400, and then the second year at $43,800, third year at $65,200. And if you take that all the way down to 10 years and you divide that by 10, you're looking at about $22,400, which is about $140 an acre. That's prohibitively expensive for corn. So typically when guys are using sulfuric acid, they're only using it when they're applying fertilizer so that the bicarbonates in the water aren't tying up the fertilizer that's in the water when they're fertigating. But if we're wanting to use it all the time, then because our bicarbonate levels are high, or because we need to keep things clean, the initial cost of a sulfur burner is in this $30,000 range. We're looking at spending about $3,000 a year on sulfur. And if we extrapolate that down, our yearly cost at 10 years is about $6,100, which is $38.13 an acre. Nobody wants to spend $40 an acre either. But I want to go back to the yield loss that we saw in our pivot ground up here. That was about 30 bushels an acre is about what that yield difference was the year that we had good rain outside the pivot and inside the pivot. And so if we look at this cost of $38.13 an acre, and we look at the yield loss that we accumulate over the years to the point where we're losing 20, 30 bushels an acre every year. So then this $38 an acre really is more of an investment to protecting those bushels, so that we're not over time losing that yield. And again, if we wanted to use AMS to get the same result, we're looking at about 312 pounds of AMS per acre, and that ends up being about $62.50. And that would give us the 75 pounds of sulfur that we need to put on per acre. So that kind of finishes up this portion of my presentation. I'd like to talk just a little bit more about water, and I want to use a demonstration to do that. What I've got here is some water from a local well that's pretty hard, and the bicarbonate level of this water is about 350. A lot of times when we think about water and it's clear, it doesn't look like there's a lot. What I want to do with this demonstration is to help us all visualize how much is in water, and then I want to show what the treatment of that water will do to get rid of it. So I'm going to put water in this tube here. I'm going to add anhydrous ammonia, and that's going to very quickly precipitate all the bicarbonates that are in here, and we'll be able to see that. We'll be able to see how much is in the water. Then I'll take the water out. I'll put some fresh water in, and then I'll add some sulfuric acid to it to get rid of the bicarbonates or liberate those. And then again, I'll put some anhydrous in, and you'll see that that there's no bicarbonate precipitation. So I'm going to go ahead and get started here. Thank you.
One thing I would add while Koertland's doing this, so in the past, the only way that we could measure or know the effect of bicarbonate in the soil was to look at calcium availability. So back to that slide I showed, looking at what the H3 calcium was. Just this last week, we found a lab in Lincoln, Nebraska that can actually test and measure bicarbonate in the soil. So up until now, we were not aware that we could do that. We now have a source that says they can actually measure bicarbonate in the soil. Other labs could do it on a calculated basis, but nobody was really measuring it, a true measurement. So that's something we're going to be looking at this year is the measurement of bicarbonate in the soil.
Okay, I'm going to go ahead and add this anhydrous here. Oh, there. You can see this cloudy. This is the bicarbonates precipitating here in the water. So if we let this sit, these really small crystals will turn into big puffy crystals that look a lot like snowflakes.
And that is why anhydrous, so when we first started irrigating, we asked some questions, why can't we apply anhydrous through a center pivot? And they said, well, it'll plug it up. Well, this is why. This stuff would plug up a center pivot really quickly. So that's an interesting side note of what that does. I mean, that's a lot of stuff in there that you can't visually see until you precipitate it.
Mm-hmm. So during this next test, I've got a CO2 meter here, and this tests the ambient CO2 in the air. Right now we're at about 660. And we're just going to use this again to demonstrate that when I put the sulfuric acid in, we're going to see that there's going to be CO2 that comes up off of here, and we'll be able to see that on this meter here.
So one of the things looking at that cloudy water, the best way that I know to think about bicarbonate is think of it as glue. Well, I look at that cloudy water and I think, in my mind, I picture Elmer's glue, and every time I water, I'm putting glue in my soil. And that glue is glue and soil together. It's grabbing calcium. It's making soil stickier. Your water infiltration gets less and less. It causes all kinds of problems to just continually put that out there and not address it. So again, it's kind of a hidden issue that we think is limiting a lot of producers, and this applies for center pivot and for drip the same. It's an issue on both.
Okay. Yeah, if you want to stick that on there. I've got just a little bit of sulfuric acid here. Ready?
So we're at 690 right now. $700, so it's starting to emit that CO2 starting to come up out of the water.
It's really hard to see just because the bubbles are so small and they make their way up through the
720, 730. So that's what happens to the bicarbonate. It leaves as carbon dioxide. 740. Now it's starting to kind of flatten out there around 740, 741. So that's where the bicarbonates go. It's a simple chemistry reaction.
Yep.
It's starting to drop back down now.
Okay. So that reaction is complete. We can add anhydrous now. And a little bit of snow came off there from the stuff that was on there. And you can see the anhydrous going into the water. But matter of fact, before it gets, anhydrous is going to be coming out the top here too. So yeah, I'm going to go ahead and shut it off. But as you can see, the water is clear now, and so that bicarbonate precipitation reaction didn't occur, and this is why we tend to use acid to treat the water, because it's relatively inexpensive and it's and it works very well. So, does anybody have any questions about that?
So
Okay.
Koertland is our in-house water guru. So if you have a water sample and you want to sit down or call Koertland sometime and go over what your water looks like, that's his specialty, and that's what he's here for, is to help you understand what your water looks like, what it's doing in the soil, and we're continually learning more. We've got new technology we're looking at this year, with nano bubbles and different things that we're looking at. We're continually looking at new technology and what's available to make water do more for us. And this is certainly part of that, is the bicarbonate issue. So